Hi and welcome. In this video, we continue our discussion on probability theory and focusing on joint probabilities. Most of the times, we need to calculate the probability of two events happening together or the probability of one event happening taking into account the happening of another event. For example, the chance of scoring above 90 in an IBT TOEFL test, given that someone has taken an intensive preparation course, or chance of getting A- in statistics and a B+ in ITC 255, or chance of arriving on time given that there is a planned demonstration, or chance of raining given that the USD Afghani exchange rate has gone up, or chance of finishing on time and finishing all activities planned for a workshop. To study such problems, we first introduce joint sample space. The joint sample space is a set containing all possible outcomes of a joint experiment. For example, if you consider scoring above 90 and taking a preparation course, we are dealing here with two experiments. First of all, taking an exam and then taking a preparation course. The sample space for taking an exam is scoring above 90 or 90 or less. Let's denote a score above 90 by A, 90 or less by B. And then the sample space of taking a preparation course is preparation yes or preparation no, denoted by 1 and 0. Then the joint sample space of this joint experiment is S1 times S2, which is the Cartesian product of S1 and S2, A1, A0, B1, and B0. Remember that A and 1 is the case when the candidate gets 90 or above and visited the preparation course. As another example, consider tossing a coin and a dice together. You see that tossing a coin is one experiment. Tossing a dice is another experiment. When we consider both experiments together, we are dealing with a joint experiment. The sample space for tossing a coin, we know it's H and T, and for tossing a dice, we know it's 1, 2, 3, 4, 5, and 6. The joint sample space is S1 times S2, which is a Cartesian product, H1, H2, H3 up to H6, and T1, T2 up to T6. Using the joint sample space, we can calculate the joint and marginal probabilities. For example, if we consider the joint experiment of tossing a coin and a dice, the marginal and joint probabilities are calculated as follows. Here in the first row, we consider the outcomes of the dice. On the first column, we consider the outcomes of the coin. Then we have HN1 with the probability of 1 over 12, HN2 1 over 12, and so on and so forth. On the margins, we can calculate the marginal probabilities, which is the probability of the events considering the experiments independently or separately. For example, the probability of getting an H is 6 over 12, which is the sum of all these probabilities, which is 1 over 2. Remember that the probabilities, both joint and marginal probabilities, calculated with the method which we have introduced in the previous lectures, namely Monte Carlo simulation. For example, the probability of joint event HN1 is 1 over 12. Probability of TN6 is 1 over 12, and probability of T and odd is 3 over 12. Continuing along the same line, if the happening of one event provides information about the probability of other event, in this case we can calculate the conditional probabilities. The conditional probability of E1 given E2 has happened is the probability of E1 and E2, which is a joint probability divided by the probability of E2. For instance, suppose E1 is 1, 3, and 5, which is getting an odd number when we toss a dice. In E2, 1, 2, 3, which is a number less than 4, again in the experiment of tossing dice. Then the probability of E1 given E2, in other words, the probability of getting an odd number given E2, in other words, we know that the number which has come up is less than 4, is equal to the probability of E1, E2, the joint probability divided by probability of E2. We know that the joint probability of E1, E2 is 2 over 6, which is 1 over 3, and the probability of E2 is 1 over 2. Dividing this gives us 2 over 3, which is the probability of E1. In other words, getting an odd number given the fact that the number is less than 4 is 2 over 3. Based on a large number of observations, we know that probability of arriving on time is 0.8. And the probability of traffic jam is 0.4. And probability of arriving on time in traffic jam is 0.1. Now we can calculate the probability of arriving on time given the traffic jam, which is 0.1 divided by 0.4, which is 0.25. This means that if there is a traffic jam, the probability of arriving on time is 25%. Two events are called independent if the happening or not happening of one of them does not provide any information about the probability of the other one. In other words, the conditional probability of A1 given E2 is the same as the probability of E1. That means the happening or not happening of E2 is not relevant to the probability of E1. As a result, the joint probability of E1 and E2 is the probability of E1 times the probability of E2. For example, if E1 is getting a hit and E2 is getting 1 and tossing the dice in these two experiments, then probability of E1 we know is 1 over 2 and probability of E2 is 1 over 6. Therefore, the probability of E1 times the probability of E2 is 1 over 12. On the other hand, we know that the joint probability of E1 and E2 is also 1 over 12. Therefore, E1 and E2 are independent because the joint probability of E1 and E2 is product of their probabilities. If E1 is 1, 3, and 5, then the probability of E1 is 1 over 2, and E2 is 1, 2 over 3. Therefore, the probability of E2 is also 1 over 2. Hence, the product of the two is 1 over 4. But if you find the joint probability of E1 and E2, we get 1 over 3. And since 1 over 3 and 1 over 4 are not the same, therefore E1 and E2 are not independent. Thanks for watching and good learning.